Log on, tune in, find out. Another good idea from Cambridge.
It's Kate Chen from the University of Liverpool. He's going to talk to us about a new multi-modality model for effective intensity standardization and image registration.
Thank you, and good afternoon, everyone. And it's a pleasure to give a talk here to summarize some work we did recently on image registration. I have a research center in Liverpool specializing in developing new techniques for mathematical imaging. So we deal with several projects, early ones on denoising, deep learning, in-painting, segment registration. At the moment, three projects are ongoing, blind deep learning and registration segmentation. So we have a few collaborators, some are located in Liverpool, others are former students. They come back regularly to work with us. My recent collaborators include Tony Chan, Raymond Chan from Hong Kong. Tony was here earlier in the week, and that's when my work in this field started when I visited UCLA many years ago. This particular work is joined with my former student, Carlos Brito from Mexico, and that's Nopadol Chomchom from Thailand. Okay. So we are newcomers to this field. There are a lot of excellent work in this field, and David Hawkes was here earlier, and then Derek Hill did some excellent work we heard this morning on non-rigid registration using B-splines and so on. And a lot of variational stuff are covered by Jan Madetsky, the two excellent books. And so our first work in this field was using mean curvature regularization to register two images. And that was appeared in last year in some imaging sciences. So that's for denoising, and then we apply this work to registration, and then it came out this year. Okay, so today I mainly talk about a little bit of this work here, and then to concentrate on multi-modality. So the multi-modality, the main like a mainstream method is using mutual information, try to do the fidelity. But we found out there are applications where this is very sensitive to use and it's not reliable. But for brain imaging, it's pretty good. For others, it's not. So, and then actually, some of these ideas we tried come from Jan Madetsky himself. I think there are two ideas, as far as I know, avoiding mutual information. One is where Professor Haber, he was here earlier, and he worked with Jan Madetsky. They use gradient instead of intensities. And then there was another idea using homogenization, which is the one we took up. Okay, my outline follows. So first, just give you a quick introduction on what image registration is about, and then talk about this new idea used for the monomodality model, this new fitting term, and then talk about for the multi-modality case. And then finally, if I have time, I'll show you some generalizations we have done recently for sequence images. Okay. So as you all know, and then for deformal registration, we are given two images, R reference and template. We try to co-register them, and we are looking for a general. This is not parametric registration. If you assume we want to find general transform phi, so that, or you can write phi as x plus u, use the displacement field. so far is a general function, and then we want after this registration, the new this transform template is close to the one of the image reference image. So here I have two guys. Is the other one here or not? Oops, not here. Okay, I have a picture in PowerPoint, but this is PD. So the registered image should look like R. So that's the idea. So this is for the single modality. So for variation formulation, so we have this fitting term, as I just mentioned. We have this image given, it's just leave where it is, and then this guy try to deform to match, to minimize this SSD distance. And then you have to impose some regularity, and then there are different choices to talk about next. So what are the choices? We heard about from David Hook's talk this morning, elastic models as one of the early ones. You can do the diffusion model. This is like H1 semi-norm, and optical flow, and you can do some proximate curvature. Yes, these are Laplacian-like regularization. You can use a total variation. You have if you have a non-smooth deformation field, and then this is the mean curvature model we tried last year, and this is based on Chen and Zhu's idea for denoising, and that was very good. So if you are not familiar with the mean curvature regularization for denoising and then separation and registration, so the main advantage of mean curvature study for denoising is that it can preserve this the jumps, and also it can give nice recovery for the smooth images. So it has the benefits of the TV, but without staircasing, basically. So why is this model not popular? The reason being, although Chen Zhu published this paper preprint in 2008, not many people use it, because if you look at the formulation, the ER equation is fourth order, highly nonlinear, and there were no numerical methods which can converge for it. It's highly nonlinear, so the fixed point methods, Newton type, all these methods don't work at all. So what they did in Chen Zhu was use gradient descent. For a typical image, say 256.256, you really need about 20 hours of convergence, fast laptop. So it's really slow. So no one can touch this this regularizer. So what we did in this paper, 2010, was to find a way we find a new way to find a new iterative solver as a smoother to design multigrid. So that works very well. Okay, so here I want to just show you for the monomodality, single modality, to see what's the result like when we use the mean curvature regularizer. So here, what I got here, my comparisons are, this is the diffusion or elastic. I have two examples. So this is like a smooth case. So this is reference image, template. The second example, this is reference and template. We try to co-resolve these two. For the first case, I have this diffusion or elastic models. This one doesn't work very well, the diffusion model elastic. The reason being the deformation is too large for it. And so for the TV model, because TV is designed for non-smooth deformation, this is very smooth. TV not doing very well. So the only two models that worked well are the Modesky's curvature model, the other Laplacian, that's fourth order but it's linear, and the Hand model, two curvature models work very well. So this is the result against this reference. But for the non-smooth case, and then the TV model gives an excellent result. You can think about medical imaging where you have a bone, say broken bones and so on, and the TV will give you a nice registration. All the other models doesn't give you a very nice results. So this new curvature model, you can see in both cases it gives you a very even visually you can tell. You can check the check the SSD distance. But these are very good. That's why we recommend this. Okay, so let me come to the main topic for the multimodality case. So what's our idea? Our idea is this. What we got here? We are given two images R and T. They have different intensities. We can't use the L2 distance, the SSD. So what do we do? So we can't use this guy because it doesn't make sense because they are they have different intensities. And in the extreme case, for example, CT against ultrasound, some of the dark areas, black, correspond more bright in the other image for the same feature. It's not always like this. So that makes this the wrong model to use. So the homogenization idea is this. This is the original Montesquieu suggestion. You multiply this and some suitable function C. It's like a scaling function, okay? So you scale the intensity to one of them and then co-register. And then you have to find this C somehow. So they suggest use the diffusion H1 regularization in this framework. So you have this kind of generalized SSD for the fitting, and then you regularize the deformation and also this homogenization coefficient. So what we tried this idea also, and then we also propose this model 1, which is instead of multiplying, we add this unknown homogenized function in the whole domain, and then regularize in the same framework. And they are very much related. What's new to us is we found out if you in choosing the regularizers, if you use the total variation or the simple H1s, the results are not always good. So if you use the curvature for both, they give you excellent results. Okay. So I don't want to show a lot of math because they are very involved. So what we got here? So this is our second, the first model. So what you see here when you find the ER equation, you have this is the fitting term that's standard for the SSD, okay. And for these regulizers, so this is for the displacement. That's first direction U1 and U2. You have this fourth order terms here. That's nasty one. That's why people don't use this kind of model. For denoising, we also have this kind of singularity. And this one doesn't come out very well. So for this correction or homogenization term, we also have something very similar. So we have a similar kind of singularity here. And then what we do is we need to solve these equations in a fast way. We had developed two methods for it. One method we called operator splitting. Operator splitting here I'm not presenting, I will just show you the second method. Is if you linearize this thing and find a simple iteration, it wouldn't converge. We tried also combinations. For example, you could say all the nonlinear coefficients like this guy should be frozen, and so on. You should linearize, try to do the inner-outer iteration. There's no convergence at all. And so what we did was you add operator both sides. It turns out to be a total variation operator, and then you linearize, iterate. That converges. That's one way. And so the next way I want to show you this prime deal idea. So what I had we have done is introduce this intermediate. It's like the mixed finite element. You introduce this intermediate variable, which is the mean curvature, v1, v2, and then you rewrite a main PDE as these 6 guys. So these are the equalities. So the g's are 0 on the, we are using multigrid. So g is 0 here. And then these are the equalities, and these are the reformulated second order PDEs. And then we linearize this guy, and then we develop multigrid for it. So it will be nonlinear multigrid for these 6 PDEs. Okay. So here I want to show you some results we have achieved using this homogenized model. So here I have two MRI guys, and then the registration results pretty good. This is retinal imaging, and more MRIs, and these are the two different hands. This is very, very slim. This is the fat one, different intensities. So the regular results visually looks good. And I'm sure you ask, how do you compare with the state art, which is the new multi information? So here we need to do more tests. And this is the reference image, and this is the template. I think these are like coming from T1, T2 of MI, and they look quite different in the intensities. If you use SSD, you get a clear this is wrong compared to the R. And then if you look at mutual information, it's a bit better than SSD, but it's still not very good for this case because this deformation is quite large. So therefore, when if you look at our results here using this like our homogenized SSD, they give a very similar error. These two almost like very good. Or I call our method to be standardization method, meaning that we can still use as a mutual information model, but don't just use it directly. We use our model to work out this C homogenized function, and then to modify the template image, and then apply this idea of a mutual information model. We get similar results. Okay, so the results looks good. It improves on this is the mutual information model. Right. I want to talk about this briefly. How to generalize to a sequence of images where you want to find common features in a sequence, say MRI. This is taken from Gun and etc. Their paper. Here this is for finding the here we call it is IRG method they recommend. If you're given not just two images, a sequence image, or if you are given two images, you want to find a compromise. You don't want to register each other. You want to register somewhere in the middle, and so that this guy, hopefully this spline field will be both smaller, and this middle guy will be some kind of average. Okay, so we want to use our ideas to this kind of scenario. So how do we do it? This is for atlas given with similar intensity. In other words, where SAD is suitable. So you can. So the way they do it is propose you cross-register each of them to the to each other, and then you want this difference to be small. In other words, all images you allow it to take some displacement, and so this is it's not very clear. This image I, image J, they both you plug this displacement, the other one as well. You want this transform image to be close, and then you do it for all of them. Therefore, you do the I, J loops. And then clearly, if these guys are from multi-modality images, you can't do this. This is not suitable. So this is where we want to use our idea of these homogenized functions to compensate and then apply this framework. Okay. So this is a simple application we only tried very recently. So we have two models. Actually, we recommend the first one. So for each image, and then we this registration part, and then this is the correction, intensity correction, and then so globally this is the fitting terms. We want all of them to be after registration to be close to each other, and then we want these guys to have a minimum some regularity. Here for as a test, we haven't tried curvature in this case. We expect this thing to work. We tried actually, I think the total variation we tried for one of them. Right. So what I tried here, we tried for the displacement field for each pair, we make sure this is Laplacian of this guy. In other words, this modify the curvature to be minimal. Also for the correction field, we homogenize the terms without the total variation to be small. Okay. So that's just simple generalization, but we made a simple choice just to see how this idea generalized. So other than we have so many PDEs, depending how many images are given. So this is like equation set I. So you have this is a first order PDE here for the two displacement direction U1, U2, and then you have this is the TB term for the correction. And so we have all the PDEs. Now, I want to show you the result we have obtained recently. As I said, if we use Geng and their work without modifications, so here we are given 4 images. This is 1, 2, 3, 4. You want to find something common between them, and obviously the first one you can see has a very different intensity from the other 3. If you just apply that model without any corrections, you get something like, almost like a circular, but they are, this one definitely different from the other guys. So we call this a very poor result. Now, if we use our new model, so we are given these 4 images, and then you cross register each one. We register to this implicit image, which are very close to each other. So I think that is encouraging. So what we hope to do is really do the curvature regularization for all the terms, which is something we want to try next. Okay. I didn't prepare a long talk, so I want to make a summary, and then if you have questions, you can ask. And for the monomodality registration, our favorite recommended method is using high order regularization rather than low order and proximate curvatures. For the multi-modality, and then this idea of standardization based or homogenization based ideas, it's non-mutual information based, it's feasible, reliable, and it's also for atlas images. It looks very promising. So what we want to do next is we study this in a 2D setting. We want to move on to 3D, and then we are to work with talking to local hospitals, try to apply to some more real data to hopefully for them to use this work. Thank you.
Any question? Is there any physical relevance to this parameter C that you introduced? Can you some sense of it in terms of
the parameter C? It's more mathematical than physical. It's intuitive, isn't it? So we want this, because these tools, you can't take the error to distance because they are vastly different. So you want to like scale one of them, and then so that they're comparable, and then you do the registration. But maybe it hasn't got the physical meanings.
And how stable is it once you run the numerical calculations?
It's quite stable, yeah. It just if you don't use the curvature regularizer, for some the curvature regularizer is very robust. If you don't use it for depending which kind of image you work with, for large deformations, some of the local, I call the local or small deformation models like elastic models, they don't they can't do the registration. So if you use the curvature regular, that's very robust.
So in the first equation, you have this Ax plus Ux plus Cx.
Yeah.
So suppose you have two images where one is brighter and the other is not. So there is a contrast there. So
But
C
you
probably
okay.
would give you a contrast function. So you make the contrast equal and try to use it. So that would be that would be the interpretation. The second thing is also you can think about it as an multiplication constant, so that they look similar, and then you try to match.
You would have to adapt the formulation depending on the type of images.
Yes, yeah,
Yeah.
sure.
Obviously, if you want to make a link, it's almost like you have the machine here, you try to tune the contrast somehow, but this is automatic tuning.
Yes.
Yeah.
Is there questions? If not, let's thank.